Hello. So in this video we're going to talk a little bit about mechanical equilibrium, and this is our second chapter. Let's go ahead and get started. So an object in mechanical equilibrium is stable without changes in motion. Things that are in balance with one another illustrate equilibrium. You can think of this as stacked rocks on a hiking trip, or maybe playing the game of Jenga, or your sibling stacking blocks. As long as they're in balance, they can illustrate equilibrium. And things, like I said, that are in mechanical equilibrium are stable without changes in motion. And so as long as there continues to be no changes in motion, those objects are in mechanical equilibrium. And so these rocks here are an example of mechanical equilibrium because they're in mechanical equilibrium. So as soon as you apply an unbalanced external force, you can change their resting state. You give that stack of rocks a nudge, you're applying an unbalanced external force that would be needed to change the resting state of those blocks. So you might, create a little disorder, cause the blocks to crumble and fall. Well, once they do, they'll once again establish a new resting state. Force. Force is needed to change an object's state of motion. Otherwise, the object will continue doing whatever it was doing before. So if you want to change what an object's doing, some force is needed to be applied. A force is a push or a pull. A force of some kind is always required to change the state of motion of an object. The combination of all forces acting on an object is called the net force. The net force on an object is what changes its motion. And we'll use the scientific unit of force, which is going to be the Newton. We're not going to use foot-pounds. Okay, so just as an example, we have a free body diagram. So you could draw a box, and in that box you can draw some different vectors coming off of it. So in this example, we have a 5 Newton force to the right and a 10 Newton force to the right. So ask yourself, what is the net force of this example? And so you would simply combine those two vectors. And the resultant vector would be 15 newtons to the right. Combination of those two vectors would give you 15 newtons to the right. Or in other words, the net force is 15 newtons to the right. So remember, we need both magnitude and direction for vectors. Another example is we have two different vectors in opposite directions. One is 5 newtons to the left and the other is 10 newtons to the right. And as we combine those into a single net force, the resultant vector is 5 newtons to the right. In another example, we have two equal and opposite vectors, equal and opposite forces. And so you should be able to answer this question. The resultant net force is going to be 0 newtons. Okay, in this example, a person is holding a rock, or a yellow ball is what it looks like, and they are resisting Earth's pull. This gravitational force that we say is resisted by the strength of this person. Their balance and their strength is resisting Earth's gravitational pull. You can also have other ways to exert a force. So you can think of a stretching spring or a stretching string or anything else like that, exerting a force that we would call tension. Pounds and newtons are both units of weight, and units of weight are units of force. So in this example, we have a tension scale, and this tension scale is going to read both pounds and newtons. And the upward tension in the string has the same magnitude as the weight of the bag. So for example, if we have a bag of sugar that weighs 2 pounds, we could say that it weighs 2 pounds, we could say that it weighs 9 newtons. Weight is the force exerted by gravity. And the same amount of force exerted by gravity, since this is in mechanical equilibrium, is going to be the amount of tension that we have on the scale. And we know it's in mechanical equilibrium. How? Because it's not falling. The fact that it's suspended on this tension scale, we know that it must therefore be in mechanical equilibrium. So we know that this supporting tension force must also be the force exerted by gravity. But something to note, we're not actually measuring force exerted by gravity. We're inferring that because we're measuring the amount of tension that's created by suspending this object. So we're indirectly determining the amount of weight that's being created, the amount of force that's being created by gravity based on how much tension is created by this tension scale. And similarly, on a regular scale that you stand on, you're not actually measuring how much you weigh. You're measuring how much support force is generated, and that'll allow you to infer how much you weigh. So there's two forces acting on the bag of sugar, like I said, the tension force acting upward and the weight or gravitational pull acting downward. Those equal and opposite forces are going to give you a net force of 0 because it's remaining at rest. The fact that the bag of sugar is not falling or flying up through the air, it must be in mechanical equilibrium, so it must be at rest. All right, I'm going to try to pick up the pace because I'm not moving very fast. Force can be described with a vector, and it has to be described with a vector because a force includes both a direction and magnitude. And so if you omit the direction or magnitude, it's not going to make any sense. A vector quantity needs both direction and magnitude for a complete description. So force is an example of a vector. And we'll talk about other examples of vectors. And I actually have another video, and I'll probably post a link to that, where I give a more detailed explanation on what a vector is. And so if you've forgotten what a vector is, if you've forgotten what a scalar is, please see that other video. Another important thing about vectors is to make sure that they're scaled properly. So in this case, we might say that 1 centimeter of length of arrow represents 20 kilometers per hour as a vector of velocity. And so if you wanted to show 3 times that, you might make a vector that's 3 times as long to denote 3 times the magnitude. So how do you change an object's state of motion? And the answer is to apply a non-zero net force. And you can express the equilibrium rule mathematically as the sum of all forces is equal to 0. Sigma F equal to 0. And that just basically means all forces that are acting on an object, we're going to add those together. And if they equal 0, we know that we are in equilibrium. Mechanical equilibrium is a state where no physical change in position occurs. Whenever the net force of an object is 0, the object is in mechanical equilibrium. This is known as the equilibrium rule. I'm going to jump forward a little bit. For example, we might have these two gentlemen standing on this scaffolding, and the scaffolding is in equilibrium. We know this because they're not falling. All right? We can add up their forces due to gravity. So the scaffold has it, each of these people has it, and you could add those together to create a total magnitude. And that total amount of down arrow, that total amount of magnitude, should equal the amount of support force, or the amount of tension force in this case. It's where supported by these cables. We would say the support force is the tension force, and the sum of one of these two vectors should equal the total sum of the downward vectors. They should be equal, and obviously they're opposite. The sum of the upward vectors, like I said, should all equal 0 for the scaffold to be in equilibrium. The fact that it's not falling or flying upward, we know it must be in equilibrium. All right, so I want you to think for a minute. If a gymnast is hanging with her weight evenly divided between 2 rings, how would scale readings in both ropes compare with her weight? So if you somehow were able to attach in line with this rope a tension scale, what would those readings say relative to her weight if she was just to stand on a scale, for example? Right? And what would happen if she was to slightly lean on one ring, use most of her strength to use one ring to suspend her weight? And so you should have answered that in the first case, the reading on each scale would be half her weight. So in other words, if you were to add up the total reading on the 2 scales, it should add up to be her total weight. And if she was putting more on one or the other, one scale would read more than the other, but you should still be able to add them together to get her total weight. How can you express the equilibrium rule mathematically? And that was that equation. There it is again, in case you forgot. Sigma F equals 0. The sum of all forces is equal to 0. That means you're in mechanical equilibrium. Okay, support force. So when you stand on a scale, just adjusting this, when you stand on a scale for an object to be at rest on a horizontal surface, the support force must equal the object's weight. Like I said, when you stand on a scale, the scale is not telling you how much you weigh. It's technically telling you how much support force it's requiring to keep you from falling through the scale or through the floor. All right, that would be your support force. And it has to be balanced. If it wasn't balanced, you would either be sinking into the floor or you would be flying up into space like Green Goblin. And so the fact that that's not happening, you must have balanced forces, which means the force read on the scale is also equal to your weight. What forces are acting on a book lying at rest on a table? So if you have a textbook near you, or you have some other book near you, your favorite book, the forces that are allowing that book to lie at rest on the table, one of those, force due to gravity. That's the weight of the book. But there must be another force, because if we only had gravity acting on the book would be falling through the table. And so there must be a resistive force keeping it where it is at rest, and we call that support force or normal force. Normal force is more the scientific physics word for it. So the table is pushing up on the book as much as the force of gravity is acting to pull the book downward. If it wasn't for that, if it was only support force acting on the book, you can imagine the book would be flying around like in this picture. Or if it was only force of gravity, the book would be falling through the desk. And we know that physics doesn't behave that way, luckily. And so, but it's kind of fun to think about. Remember, that's called normal force. So I talked about scales, I talked about the weight of scales, I talked about support force. So a question for you: if a person is standing on a bathroom scale, if a person is standing on a bathroom scale that weighs 110 pounds, what would the net force on the bathroom scale be? All right, and this is a trick question. You could easily just say that, well, the amount of force that's requiring is going to be 110 pounds of force. But recognize that support force is going to be balanced with weight. Otherwise, you'd be falling through the floor. So the fact that you're not falling through the floor means that the scale's at rest, which means that the scale is reading a net force of 0. Suppose you stand on 2 bathroom scales. So you're spreading your weight between 2 scales. I invite you to try this at home if you have 2 scales. And as you stand on 2 scales, you'll notice that the sum of the 2 scales is going to also read your total weight. So if you stand on 1 scale, it might read, say, 100 pounds. And then you divide your weight between 2 scales. You should be able to add up the 2 scales to give you the same weight. And that's because the scale is measuring support force, and you should be delivering half of your support force to each scale. And you can kind of lean back and forth between the 2 scales, and you'll see that the support forces can still be added up in any of those configurations to be able to get that same amount of total. I think that's a lot of the stuff that I wanted to cover. Let me think of anything else. Oh yeah, we wanted to introduce dynamic equilibrium. So objects at rest are said to be in static equilibrium, whereas objects that are moving at a constant speed in a straight line are said to be in dynamic equilibrium. So we have static equilibrium, which means you're stationary, and dynamic equilibrium, which means you are in motion. And if you're in dynamic equilibrium, it means you're moving continuously in a straight line path at the same speed with no changes in motion. So in other words, this is along with Newton's law: an object in motion stays in motion until acted on by an external force. Once you're in motion, if there is no net force to change your state of motion, you're in equilibrium, and you continue just like that until something acts on you to slow you down, like gravity or drag or something, friction, whatever. So if you were to push on a desk and there was to theoretically be 0 friction, it would continue sliding forever at that same rate of speed until some force acted on it to change its rate of speed. So friction is a constant force between objects that slide or tend to slide against each other. And this makes this is what actually makes reality, is the fact that friction exists, and it keeps this crazy perpetual motion from happening. Anytime you move something, it's going to get slowed down. You can throw a ball as hard as you want. Eventually, it's going to stop. And that's because of drag and friction. I think this is the main things I wanted to cover. We already talked about vectors. Just remind yourself that you can denote magnitude and direction with vectors. Also remember that if you have tension divided between multiple tension scales, the sum of the 2 vectors would give you both your support force or your tension force on a single rope, and also it would tell you the force of gravity acting on you. Well, thanks for watching. Don't forget to subscribe.